So in our last lecture we introduced the Hamiltonian, okay, and here you see I'm going to work in 1D. So I have written everything in one dimension. So this is the Hamiltonian in 1D, okay, and now let's work on some examples. How about let's take a 1D example of a spring mass system. So there is spring and there is mass. What is the Lagrangian of this spring mass system? We all know that Lagrangian is half m x dot square minus half k x square. Now we know that omega is equal to root over of k by m. Okay, now what will be the Lagrangian equation of motion for this? I'm not going to write it. Let me just tell you. The Lagrangian equation of motion will be mx double dot is equal to minus kx. And I said Lagrangian equation of motion will always give you the force equation. Okay. Now what happens when we find the Hamiltonian of a system? Okay. Now the Lagrangian of a system is equal to T minus V. The Hamiltonian of a system will turn out to be T plus V. Let's find the Hamiltonian. Okay, what is Hamiltonian? H is equal to P x dot minus L. Now what is P? As I defined, P is del L by del x dot. Okay, so what is L? This is our L. So if you do del L by del x dot, what you will get? You will only get m x dot. Agreed? So let's find the Hamiltonian. H is equals to, so our P turned out to be m x dot and there is a separate x dot, so this is m x dot square minus the Lagrangian. The first part will be minus half m x dot square and the second will become minus and minus will become plus. Let's see, yeah, it will become plus half k x square. So what do you get the Hamiltonian? The Hamiltonian turns out to be, so m x dot square minus half m x dot square. It is like 1 minus half, so you'll get only half m x dot square. You see there is a plus sign, plus half k x square. So it looks like the kinetic energy gets added to the potential energy. Okay, everything is good till now. Now you would ask, okay, you said that we can define the Hamiltonian of a system, and we have defined the Hamiltonian of a system, which in this case is a function of x and p. How it is a function of x and p? We have to write it in a proper way. So this Hamiltonian H can be written as p square divided by 2m, this is the kinetic part, plus the potential part, half k x square. So once we define the Hamiltonian, the next question is, what is the equation of motion for this Hamiltonian? You know there is an equation of motion for Lagrangian. What is Lagrangian equation of motion? As I said earlier, it is d by dt of the canonical momentum. So what is del L by del x dot? Del L by del x dot is canonical momentum minus dl by del x is 0. So this is the equation of motion for the corresponding Lagrangian. This is the general formula. Now what is the equation of motion for Hamiltonian? Well, Hamiltonian equation of motions are, so I'm just writing it, okay, there are long derivations for this, so we don't need that. P dot is minus del H by del Q. You see the beauty, we do not have any second order, we have only first order differential equations. And Q dot equals dH by dP. Okay, so if you solve this differential equation, what is the equation we found? For the spring mass system, we found mx double dot is equal to minus kx. This is what we found, and we know the solution. The solution in the end will be turn out to be a sine omega t, because this solution a sine omega t will satisfy this equation. But the question is, what happens when we use the Hamiltonian and Hamiltonian equation of motion? That's the question. So let's do it here. Okay, so what is Hamiltonian? Our Hamiltonian is here. Let's find P dot. P dot is minus del H by del Q. So del H by del Q, what is the Q here? Since we are doing for 1D, so it is actually del H by del X for 1D. Okay, so what do you get? Put the potential, put the Hamiltonian, you will get minus kx. Remember, x is a function of time. Always remember that x is a function of time. Here this x, and here this x. Here this x is a function of time. Okay, always remember that, because as the mass is moving under the spring, it is continuously changing its position with time. Okay, so what is P dot? Now P dot is dP by dt equals minus k x. Remember, x is a function of time. So what is P? It will become minus k integration x as a function of time dt. Okay, first thing is clear. Now what is the second equation? Second equation says q dot is del h divided by del x. Remember, as I said, 1D. So what is Hamiltonian? You know the Hamiltonian. Apply on it. Only the half kx square will be applied. So you'll get k into x. So this is not q dot, since I specified that we have to use what? Since we are working in 1D, it's better we use x dot. Okay, so what do you get? You get x dot is equal to kx. Okay, now what to do? Yeah, here. If your Hamiltonian now, here we made a mistake. This is P. We made a mistake. Let me correct it. So this is P dot is minus dH by dQ. Okay, and Q dot is dP. Okay, so this is P. Okay, so let me remove this. This is wrong. Everything is correct, only this is wrong. Yeah, so what is dH by dP? What is a Hamiltonian in terms of P? Our Hamiltonian in terms of P is P square divided by 2m plus half kx square. So what is dH by dP? Obviously the answer is P by m. Okay, now we will use both this formula that we got. What are the two important things we got? This is the first equation of motion, gives us this, and the second gives us this. Now we are going to combine them. Let's combine them. So you get x dot equals P by m. This is the second one. But from the first equation, you can write x dot equals to minus k. What is P? P is minus k x as a function of time dt. So you cannot take x outside, okay? M. And remember this side it is also function of t. So what do you have? You have dx by dt on one side, and as I said it's a function of t. And on the other side you have minus. Now what is k by m? So we said that omega is root over of k by m. So k by m is actually what? Is actually omega square. So here I have minus omega square integration x of t dt. Now if I ask you, tell me what will be my x such that the above equation will be satisfied. Okay, differentiation should give me the same answer as integration. Okay, so do you remember what kind of functions will give us? Trigonometric. So guess a value. A sine. Now since both sides we have either differentiation with respect to time and integration with respect to sine, so sine will be a function of t, and since there is an extra omega, I guess omega here. Okay, so let's see if this equation is satisfying this or not. Okay, so what is dx divided by dt? It is a omega cos omega t. Okay, this is my left hand side. Now let us evaluate the right hand side, which is minus omega square integration sine omega t dt, that is equals to minus omega square divided by omega multiplied with minus cos omega t. So what do I get? I get omega cos omega t. Okay, great. So our left hand side is equals to our right hand side. It means Hamiltonian equation of motion allows you to guess that this is the way the mass is moving. Let us see if our Lagrangian said the same thing. Where is our Lagrangian equation of motion? Here, of course. Look at here. Our Lagrangian equation of motion also says the same thing. So x is a sine omega t. This is how the mass will move under a spring potential, and Hamiltonian says the same thing. X is equals to a sine omega t. So this is the power of Hamiltonian. Things become a bit easy. Okay.